So in this MPSL modeling, they have two separate, let's say, portions. The first part is about irradiance modeling, is related to the projector they are using. And the second one is somehow similar to the SLA. We are curing the photopolymers. So the fundamentals is exactly the same with the SLA, but this part is a bit different since we are not using laser, we are using the projector itself. So you need to modify this part, but may use the same model with the SLA process. So in summary, we have patterns, and these patterns are reflected on the table. The pixels, if you are using a projector, the pixels will be irradiated, and we will be actually starting the polymerization process with the help of this irradiation. And obviously, the accuracy is depending on the radiation uniformity of your projector across your mirrors, and also it's about it depends on the collimation of the beam or the focusing of your beam. If you have problems with them, then that means the accuracy of your whole, let's say, MPSL process will be lower compared to the other polymerization processes. And as you see, again, we have a similar relationship between the curing depth and the depth of penetration and critical exposure values. So by, again, using such a relationship, you can adjust the curing depth and have parts actually fabricated with specific layer thicknesses. Any questions, guys, about fundamentals on mass projection lithography? Now I will yes.
Are there energy expenditures are similar with the layout process?
Similar, but you need to be using, as I said, a different material. You cannot use the same type of materials we are using on SLA materials. Since on the SLA, we are using more power with the help of the laser, but on the MPSL or mass projection stereolithography, we have less power, so your materials should have less critical exposure values, since we don't use lasers. Now we have a different version. Do you have a question, Adilcan?
Hocam, is the part fully cured after the process, or does it need more curing after it?
Yes, we need to do actually post-curing. The ones actually I have right now here is not post-cured, and you cannot feel obviously, but they are still sticky since we haven't done any post-curing operation. But once you do post-curing, there again strength will be improved, and you have no uncured resin around. So again, as in the case of SLA, we need to do some washing and post-curing processes. Now in this one, in this special type of photopolymerization process, we will be focusing on a patented technology called continuous liquid interface production, abbreviated as CLIP. This company is called as Carbon 3D, and their fundamentals are very similar to the DLP technology or mass projection stereolithography, but the difference is that they have a secondary, let's say, chemical reaction. They have an, in the next slide I will show, they have an oxygen permeable window, and by adjusting the amount of oxygen in the process, they can have a kind of a continuous interface. Although they claim that it's totally continuous, but since it's a layer-based method, we cannot obtain whole continuity. The thing is that the thickness of their layers are very low, around some 10 micrometers, I guess. So that's why they prefer to use the term continuous liquid interface production. So this is their close-up view on the fundamental region or the main critical part. So you see that they have a similar vat here. This is the vat they have. We have resin inside, obviously. This is the build plate, and this plate is again going upwards, and underneath they have a light engine. So instead of a projector, they call it as a light engine, but the thing is that, again, they are reflecting images on this, let's say, window. And the difference with respect to the other mass projection systems is that they are using an oxygen permeable window. With the help of it, they adjust the amount of oxygen here, and they can control this process in a much better way. And their accuracy is much better, and they can make use of different resins. Their material range is larger. And another issue is that they have a kind of a depth zone here. This is the depth zone, which means that we have polymerization here, polymerization performed. Yes, let me show you that video. As you can see, this part is actually in liquid state, but this region is the part being printed. And you can see that the resin is actually polymerized. Now we have chains which are connected together, but on the left and the right hand side, we have photopolymer, which is not cured, and they are in liquid state. And with the help of this special window, special oxygen permeable window, they can cure in a faster way, in a precise way. And as you see, this is their speed. Right now, a 200 diameter cylinder is being printed, and this is their speed, 200 millimeters per hour. So in just an hour, they can print about 20 centimeters. Okay. Oops, guys, I'm sorry. So this is the summary of their approach, and they were able to print parts in a shorter time with respect to the conventional, let's say, DLP systems or mass projection stereolithography systems. Any questions on this type of technology, guys? Okay. Now I want to focus on their business model. They're actually not selling their printer. They are just subscribing it to you, but it belongs to the company. This is a kind of a weird way. I don't know. I don't like it, but this is how they do it. And their cost for the materials are a bit higher compared to the conventional SLA or obviously PBF. As you see, it's around $100, which is not even equal to a liter. About 800 millimeters of their material is around $100. And they have special software, obviously. So if you sum all these, and you need to pay $40,000 per year, and also you need to purchase some materials. So that's a quite expensive system. But the advantage is that you can process various materials having much better mechanical properties compared to the conventional polymerization processes. And this is much faster. So you may be even using it for kind of mass production maybe. And as far as I know, Adidas is working with this company. They're kind of producing some shoes with them. They have special materials, and they are adjusting the, let's say, some parameters depending on the, let's say, properties of the user. Any questions, guys, about clip, about this faster polymerization technology?
Hocam bir şey sorabilir miyim? Ben bu klip teknolojisinde
Yes, yes.
solidification'ın nasıl olduğunu tam anlayamadım. Bu oxygen permeable window'dan dolayı mı oluyor solidification?
Yep, the solidification is actually the same. They are again curing the photopolymer, but they are curing it in a faster way with the help of this oxygen flowing, oxygen permeable window.
Yani lazer yok mu?
No, they don't have laser. They have a light source, a kind of a projector, like a kind of a screen underneath. this light is projected, this let's say pattern of the layer is projected on this window, and some oxygen is flowing through this window into the resin. And once you have it, then I think, I'm not an expert on the chemistry of it, but I think this way they can increase the speed of this process. So now I think it's time to focus on the last approach of photopolymerization process. It's called as two-photon approach. As you see, we have two lasers, two photons are coming from them, and with the help of it, we can produce very small products having detailed features. And these features are, as you see, these are some typical products having sizes of some micrometers. But the thing is that we don't have a commercial product actually utilizing this two-photon approach. And this was invented around 1970s. People are still doing some research on it, but it was very highly popular in 1990s. And since it's not commercialized, we don't see any kind of machine using it. And it's still in the laboratory scale. But the thing is that their obvious accuracy is much better compared to the other ones. And even they can cure some kind of ceramics with the help of their approach. And you can have a look at this paper if you are interested in two-photon polymerization. And this is their schematic. How do they do the polymerization? They need to have special optics for them, obviously. As you see, one of them is coming here and the other one is here. And with the help of these, they polymerize this resin inside the tank. This is another example. This scale bar is 1 micrometer, so you may assume that this dog has a size of actually around 5 micrometers. It's even difficult to see with your eyes. That's actually end of this chapter, end of polymerization processes, photopolymerization processes. Any questions, guys, about all these SLA, DLP, and two-photon processes? So in summary, we said that we are using special polymers. They are photopolymers and they can be polymerized with the help of radiation. And we can do it in point-wise with the help of lasers, or we can do it in layer-wise by using a kind of projector or light engine, or we may do it by using multiple lasers at the same time, like in the case of two-photon approach. But the thing is that we don't have any commercial products for two-photon case, but we do have for the point-wise and for the mass projection type of photopolymerization processes. So that's the end of this chapter. Now I will start another chapter, and that will be on powder bed technologies, powder bed fusion technologies. Actually, I would like to start with a video. Let me prepare it. Yes. Any questions before I start?
Hocam ödev tarihini böyle erteleme ihtimalimiz var mı acaba?
For how many days?
Güzel bir soru. Yani
Few
bilmem.
days, maybe. I may give you.
Güzel olur. Konuyu bugün işledik ya, ödevde bu konu hakkındaydı. Daha iyi anlayabiliriz diye düşündüm.
Okay, I will do that. I may give you more, let's say 5 days. Okay,
5
guys,
gün bayağı iyi olur hocam. Teşekkür ederim.
You're welcome. In this chapter, we are going to focus on powder bed fusion technologies. And I would like to start with an interesting project. This is from Marcus Kaiser. This is called as Solar Sinter Project. And now you'll see that he's going to use the fundamentals of powder bed fusion technology. And I would like to show you this one first and then start discussing the topics from our textbook. So this is a project actually done on a desert. They're now going to the project site. Yes. The thing is that it's a very sustainable project. They are only using sunlight and they are using just sand particles. So what it means that they have the raw energy, they have the material, and by using these two, now you'll see that he's going to produce some parts with the help of just the light and the sand particles. So what do we have in the sand particles? What is the main material?
Silica.
Silicon.
What do we have in sand? I don't hear Azijan, I'm sorry.
Silica.
Yeah. So that will be the main material for this fabrication process. Go faster. Yes, this is their equipment. They have solar panels. They have sand all the way around. Obviously, he has some electronics. And with the help of this part, he's going to focus the light onto the table. This is a table, and he has a kind of a powder bed, and the fabrication will be performed inside this bed. The electronics are not that complicated. It's just moving the focuser here. This is a panel, the focal point on the table, sound tracker, lens, battery, and some electronics. Yes, this is office. He's using some, I think, stepper motors and some belt to move that sound tracker. So now, I'm sorry. Yes, this is a table, and this is our powder bed. Inside this bed, we obviously have sand particles, and on this table, we will be fusing these sand particles together. And this fusion is actually done with the help of the sunlight here. It's focused on that point, but our accuracy is not that good. Our focus diameter or beam diameter is quite large, so we cannot produce very small products. The ones he's going to manufacture are quite large, and you will see that they're not accurate. This is for sound tracker. Now he's putting powder or sand on the next layer. Now actually the fusion started. The printing process has just started. That's a close-up view. As you see, the silicon particles are being joined together. jump to, yes, this is a layer. As you see, these parts are actually fused together. So this is a type of shape actually you want to have at the end of this fabrication process. As you see, it's always tracking the sun now. It's moving the part out of this bed. This is powder bed, and the part is ready. You see, it's not highly accurate, but it's fine. Since it's a sustainable manufacturing project, he didn't use any plastics. He just used the sun and the sand particles. It's tracking the sun again, once again. Another part is being manufactured. And after each layer, actually, he is doing some manual operation. He's pouring some powders, pouring some sand particles on it, and then sweeping it through the top face. It's quite hot, obviously. I think it should be a bit heavy. Yes, this is the end of the story. Any questions, guys, before I start discussing the details?
Hocam bu teknolojiyle ne kadar ileri gidilebilir acaba?
I couldn't get it.
Diyorum ki bu teknoloji kullanarak ne kadar ileri gidilebilir yani şu an?
I will show you now. Most of the companies are using this technology. Even they print metal products with the help of the same fundamentals. The difference is that instead of sand particles, they are using metal powders, and instead of sun, they are using powerful lasers. But the fundamentals are the same.
Hocam ben şey merak ettim. Bu kumu eritirken mercekten geliyor ya, yani güneş enerjisini kullanıyor. Ama bu sonuçta güneşten gelen ışık, yani kesintisiz bir ışık ya, böyle orijine falan giderken de partikülleri eritmesi gerekmiyor mu?
What do you mean to origin? Do you mean the levels underneath the top surface?
Yani şey demek istiyorum, herhangi bir harekette aslında sonuçta güneşi kapatamayacağına göre mesela SLS'te falan şey oluyor ya, lazer atıyor, kesiyor, atıyor, kesiyor. Bunda her hareketinde bazı materyali eritmesi gerekmiyor mu? Onu nasıl
That's
ayarlıyor?
why we always have continuous patterns. And as you see, the parts are not accurate. It's just showing the concept. So it's just showing that in desert, you can do manufacturing. But obviously, since we cannot stop the light, you may have problems if you especially want to print some separate products on the table. They need to be all connected together, since you cannot stop the light and then start it again. It's a good point, but in desert, this is what he can do. Okay, let's start discussing the fundamentals of this process. Powder bed fusion processes, we will see that there are variations of it, but the main thing is that the manufacturing process is performed in a powder bed. And in that powder bed, as the name implies, we need to have powders. And these powders should be fused together. Sometimes they might be sintered together, but at the end of the maybe some post-processing, they need to be fused together. Otherwise, their strength will be lower. And this is, by the way, one of the first commercialized AM machines, AM processes, not exactly the first AM patented, but it's the first additive manufacturing process which is commercialized. And as I mentioned, we have some variations. One of the variations of powder bed fusion process is the selective laser sintering system. And this is the first one which is commercialized. And as you see, they're not fusing, they are sintering the powders together. Do you remember the powder metallurgy process from our 202 course? We were joining again the powders together, but after that we need to do some post-processing. We need to put the parts into oven and try to increase their strength, increase their bonding between the powders. So that's why, again, after the selective laser sintering process, we need to do some post-processing. So what are the main characteristics? Obviously, we are using powders. We need to have a thermal source to do the melting or to do the sintering. Another thing, we need to control the fusion process. And further, we need to have a recoating system, which will spread the powder on the table uniformly. So this is another important issue. You shouldn't have thicker regions and thinner regions on the table. You should always have a uniform layer thickness on the bed. So this is a nice sketch showing the fundamentals. Somehow similar to the Marcus Kaiser's project. This is our actually build platform. So this is called powder bed. And this one is always moving downwards once you are done with a specific layer. After this layer is actually sintered or melted, then our system moves this platform one layer down, and then with the help of the feed carriages, as you see, this system has 2 feed carriages, one here and the other one here. And after each layer is performed, each layer is sintered, these feed carriages goes upwards a little bit, which means that we will have some extra material. So if I draw a side view here, assume that this is the feed carriage. Once you move a little bit, then that means you have some powders around, okay? And then once you have powders here, with the help of this kind of rolling system, powder leveling roller, or we sometimes call it counter-rotating powder leveling roller. This roller will move to the right, and it will spread this powder on the table uniformly. So the function of this roller is that you are spreading the powder on this table uniformly. And after you have all these powders on the table, then what we do, with the help of these, let's say, heat source, we try to join them together. We try to fuse them so that they will be shaping or making a kind of a solid part. But we are not doing it for the whole layer. With the help of this laser, again, we are using kind of galvanometers, set of mirrors. With the help of it, we can move our laser on the table, and we can just fuse a specific region. We don't want to fuse the whole slice, since we want to have a specific shape once the printing is completed. So that's why these lasers, as in the case of SLA process, they should follow a scanning pattern. So do you see an extra component here?
Heater.
Yes, we have a heater here. Why do you think we have this heater here, and what is the function of it? Can anyone tell me or comment on it?
Control environment stand.
To heat the environments, yes, somehow. And another idea?
Daha rahat sinterlamak için mi acaba?
To make it easier, you say?
Yes, so like preheating it so that the laser can heat it easier.
Yes. So if you remember from, again, powder metallurgy, for sintering or for melting operation, obviously we have some specific temperature values, right? It might be about 0.6 times the melting point temperature for sintering operation. But obviously, if you do the melting process, then you need to reach this melting temperature. So if you don't have a heater in your environment, the thing is that then all this power actually should be given just by a laser, which means that you need to have high power laser, which is highly costly. So what they do instead, they simply use conventional heaters around, and these heaters will increase the temperature probably to around, let's say, 0.4 to maybe 0.5 of the melting point temperature, so that the laser will give less amount of power, apply less amount of energy on the build plate, and will be able to again do the sintering or do the melting operation. So the full control will be on the laser, but you don't need to use high power laser. So this is the advantage of using a specific IR heater here, or it doesn't, the type is not important, but you need to have a kind of a heater here, which will decrease the laser power requirement. Another advantage of using laser is that, using heater is that you will be able to control the temperature of the environment. Since if you don't use a heater, then that means you will have, let's say, a temperature of 1000 degrees on the plates, on the build plate. It is a metal, for instance, but you will have, let's say, a temperature of 100 on the machine, which means that we have a huge difference between the powder bed and the other regions inside our machine. So this will result again undistributed, let's say, heat, and we will have uneven distribution of temperature, which will result in again some cracks, some thermal stresses, some warpage on the material, on the part. So that's why we make use of such a heater, so that the temperature inside this machine will be as uniform as possible.